Hi guys, we're going to do a video here on standard enthalpies of formation. What are they and how do we use them when trying to figure out the enthalpy change for a reaction? All right, so let's just go through this section of the thermochemistry unit. Okay, so here's what I'd like to start with here. It's just a statement. In order to determine the delta H for any reaction without ever having to conduct the reaction, scientists have developed a method let's use the term a methodology using this concept of standard enthalpies of formation. So we'll underline that term, standard enthalpies of formation. All right, so let me just back up for a minute. We have learned in the lab in this course how to figure out the enthalpy change for a reaction using coffee cup calorimetry. That's where we measured the heat of a reaction by looking at the temperature change of the solution that it was dissolved in. Then we adjusted for the number of moles of the acid in the case of the lab that we did in the course. And that allowed us to find the enthalpy change for the reaction. In the lab, it was the reaction for an acid and a base. You can do that for a reaction. However, in order to avoid having to run a reaction every single time and just figure out what the enthalpy change is after the reaction occurs, we would like to be able to figure out what the enthalpy change is just on paper without having to run the reaction every single time. All right, so in order to do that, the scientists, like I said, have developed this idea of standard enthalpies of formation. Okay, so first of all, what are standard enthalpies of formation? And then we'll go through how to use them. When we say standard enthalpies of formation, we are talking about the delta H, or the change in enthalpy. You are going to see a little circle. It's almost like a degree sign. That refers to that these were conducted, or these were found under standard conditions, which I think is room temperature and 1 atmosphere, if I remember correctly. And then the little f, which stands for of formation. So when you see this delta H, little circle, little f, you are looking at what are called standard enthalpies of formation. Now, what are these? Let's give a definition to just what this term is. The standard enthalpy of formation is the enthalpy change, so the heat exchanged, okay, so that's the enthalpy change, is the heat exchanged, when 1 mole of a compound is formed from its elements in their standard states. All right, so let us just jot that down for a minute and let's define what a standard state is, because that's not common knowledge. So let's make sure we understand what is a standard state. The standard state of an element is the state the element is in. And when we say state in chemistry, we're talking about phase of matter, solid, liquid, or gas. The state, so solid, liquid, or gas, an element is in at 2 conditions. At room temperature, which is 25 degrees C, okay, it's about, I don't know, 74 or something like that, degrees Fahrenheit, but room temperature, 25 degrees C, and 1 atmosphere of atmospheric pressure, which is the atmospheric pressure at sea level, okay? So let me go ahead and erase the board, or at least erase this top part here so we can have some room. Let's just make sure we understand what a standard state is before we even go into the rest of the definition. If I asked you what was the standard state of oxygen, Okay, the standard state of oxygen is the form that the elemental oxygen is in at room temperature and at 1 atmosphere. And hopefully you would know that oxygen exists as O2 because it's a diatomic element, and it would be a gas at room temperature and 1 atmospheric pressure. What if I asked you what is the standard state of iron? Is that a solid, liquid, or a gas at room temperature and regular atmospheric pressure? You would say, hopefully, that iron is a solid, and you would be correct. That's the standard state of iron. How about something like mercury? Mercury is, people used to be much more familiar with it when they used it in thermometers, but mercury is actually a liquid at room temperature and atmospheric pressure. So some of these we know, but some of these you might not be familiar with. For instance, if I asked you what is the standard state of something like iodine, you might not know what is the standard state of iodine. Hopefully you'll know that it's I2, but you might not know is it a solid, liquid, or a gas. So here's the way that you can tell if you don't know what the standard state of an element is. The standard state is going to be the one that has a standard enthalpy of formation equal to 0. So the way that this works is these standard enthalpies of formation are known, and they're given actually in the appendix of the back of your textbook. So if you can grab your textbook, go to Appendix 2 at the very back of the textbook. Appendix 2. And what we're going to look for iodine, okay? So go ahead, I'll give you a minute to go look for for iodine. These are all listed by the element. All right, so look for iodine and look under, I think there's 5 different forms of either compounds or elements or ions that iodine is showing here. Only one of them has a delta H standard enthalpy of formation equal to 0, and that is I2 solid. Okay? So that is the standard state of iodine. And if you think about it, it makes sense. Think about what the standard enthalpy of formation is. Just think really hard about this. It's the enthalpy change associated with the formation of a compound from its elements in their standard states. That's what that is. So here's the thing. If you are the element in your standard state already, it will take 0 heat to form you from yourself. You already are in your standard state. So the one that has a 0 is always the standard state. So just as a form of practice, let's go ahead and actually put this together, a couple of these pieces together here, just to make sure you understand this idea of standard enthalpies of formation. Okay, let's talk about carbon dioxide gas for a minute. When we look up carbon dioxide gas, the standard enthalpy of formation, go ahead, you're either going to have to look under carbon or under oxygen. I think it's going to be under carbon. But in Appendix 2 of your textbook, look for CO2 gas. And let's see, there's a lot of them here. CO2 gas. I found it. It's negative 393.5 kilojoules per mole. Negative 393.5 kilojoules per mole. Let's make sure we understand the significance of this number because you really do have to try to understand it so it makes some sense to you. This is the amount of heat associated with the formation of CO2 gas from its elements carbon and oxygen, okay, in their standard states. So we can write a thermochemical equation for that uses this enthalpy change. So actually the product is going to be the CO2 gas. That's the whole point. We are talking about forming. That's why it's called the standard enthalpy of formation. We're talking about forming CO2 gas, and the delta H associated with this is negative 393.5 kilojoules. Okay, it's implied to be per mole because we have a 1 right, it's assumed to be a 1 right there, okay? All right, So we have to ask the question, what are the elements in carbon? I'm sorry, in CO2. And the two elements are carbon and oxygen. So, but we have to write them in their standard state. So carbon's standard state, go ahead and peek at the back of your book. Look for the standard state of carbon. What you're going to find is that there are two elemental states for carbon listed. Only one of them has a delta H standard enthalpy of formation equal to 0, and that is carbon solid, but in the graphite form. So you would write that like that. And carbon plus the other element here, I see oxygen. What is the standard state of oxygen? And that's O2 gas. So the formation of a compound from its elements in their standard states, that's the heat associated with it, and that is the standard enthalpy of formation. So it might seem to you to be a little bit random and maybe not that useful, but what I want to do is show you how this is incredibly useful to scientists so that they can predict what the heat exchange is going to be for a reaction before they do it. You wouldn't want to just mix two chemicals together not knowing if it was going to be extremely exothermic or extremely endothermic. It would be quite important to know that so you don't melt the container or hurt yourself or whatever. So that is why these are so useful. So now that we've explained what is a standard enthalpy of formation, let's talk about how it's used, how these numbers are used. All right, now this actually comes back to an application of Hess's Law. Hess's Law we've been over, but Hess's Law, I won't write the definition, but it essentially says when you can represent an overall reaction as the sum of a series of steps, the enthalpy change for the overall reaction is going to be the sum of the enthalpy changes of the steps. That's what Hess's Law states. So this is really an application of Hess's Law, which is what I'm going to be talking about here. This is a Hess's Law application. Okay, so what scientists have done is they've essentially taken they've taken an overall reaction theoretically, like in their minds, through a series of steps. So what do I mean? All reactions come in the same form. Reactants become products. Reactants become products, okay? So what they've said mentally is they said, all right, let's break this down into two different steps. Let's just think about this as two different steps. First, let's take those reactants and decompose them into their elements. Whatever elements are in those compounds, let's decompose them all into their elements. That would be considered step one. And then step two is, let's take those elements and reform them into products. Like I said, this is really just a mental exercise at this point. Okay, so the scientists say if we essentially take these as steps and add these two steps together, elements will cancel because there will be the same elements will be present on both steps, of course. And so the reactants will just be turned into products, which is just your overall equation. Okay, so how is this useful? Well, if you've been following me through the earlier portion of the video, you will remember that the standard enthalpy of formation is the enthalpy change associated with the formation of a compound from its elements. So if you let's look at the second step for now. You'll see that this is kind of like a standard enthalpy of formation reaction. You have elements on the left side turning into compounds or products on the right. So if you were to think about adding up all of the if there's multiple products, adding them all up together, you could represent this this enthalpy change as the sum of all the standard enthalpies of formations of the products. In other words, if you have multiple products, you would just add them up all together, but you would basically represent this step as the sum or adding up all, and make sure you notice that word all, that's going to come into play, all the standard enthalpies of formations of the products. Now, the earlier step, the reactants becoming elements, hopefully that you can see that if we were to reverse this equation and make the elements on the left side, we're essentially also kind of writing a standard enthalpy of formation reaction. So, but remember, if you reverse an equation, you have to flip the sign of the enthalpy change. So here, we could think about this one as the negative sum of all the standard enthalpy changes, standard enthalpies of formation of the reactants. Now, Hess's law says when you take two steps and add them together, the enthalpy change for the overall reaction will equal the sum of the two steps. And if you look at it here, it would be smart of us to start with this one and then just subtract that one. And at the end of the day, even if you only followed a portion of what I've just been through, truth be told, if you can just apply this next equation, you should be fine. So the enthalpy change of a reaction is going to equal the sum of all the standard enthalpies of formations of the products minus the sum of all the standard enthalpies of formation of the reactants. And that is an incredibly important equation for thermochemistry. And let me just pause for a minute and make sure you understand what I've just told you. I've just told you, without ever entering the lab, without ever running an experiment, and without ever combining any chemicals, you can figure out the enthalpy change that you would expect. And based on the sign, you should be able to figure out if it's exothermic or endothermic by looking these things up in a table. Remember, these are known. The standard enthalpies of formations are in the back of your book for I don't even know, probably at least hundreds, if not thousands, of compounds. So we can do this all on paper, which is incredibly useful. So let's do this. Now that we've taken you through how this equation has been born here, okay, let's show you how to use it. So I'll leave that part up for now. And just ignore that. Okay, I'll leave that up for now. Let's go ahead and put a equation up on the board. So this is what a practice question would look like a type of question that you might encounter on an exam. Determine the standard enthalpy change, determine the enthalpy change, delta H, for this reaction and I will give you the reaction. N2O4 gas plus 4H2 gas yields N2 gas plus 4H2O gas. Okay, so that is all that I would have to do, is give you a reaction and ask you to determine the enthalpy change. Notice I'm not giving you anything about delta T. Okay, I'm not giving you any experimental data, no massive solution, nothing like that. However, you would have to be given standard enthalpies of formation. Either I would have to give you access to your appendix, or more than likely on an exam, I would give you the relevant standard enthalpies of formation. However, just for the sake of it, there are two species up here. You have 4 species in all. There are 2 species up here that have a standard enthalpy change equal to 0. And based on what I told you, you should be able to spot them. All right, if they are an element already in their standard state, understand it's going to take 0 heat to turn them into themselves, okay? So the delta, let me make like a little data gathering column here. The standard enthalpy of formation of your hydrogen gas is going to be 0. That is the standard state of hydrogen, so it has a 0. You could confirm that in the appendix if you'd like to, but that's in the text, or that's going to be known. And then nitrogen also. N2 is a gas. That's majority of the air that you're breathing right now is nitrogen, N2 gas. So that one is also a 0. Let's go ahead and look up the standard enthalpies of formation for the other 2 species. H2O might be under oxygen. Let's look up that one first. Yes, it is. And make sure, it's extremely important that you get the phase correct. the state correct, because each, as we noticed before, each state of a compound or an element will have a different standard enthalpy of formation. Okay, so H2O gas, in this case it's a gas, is negative 241.8. And if you look closely, you should put the unit there. It's kilojoules per mole. If you look closely at the top, it does have a unit, kilojoules per mole. So that we'll just put that there for now. Let's look for the nitrogen one, N2O4. N2O4 gas is also in the appendix 2 of the back of your book, and it is 9.16 kilojoules per mole. All right, so we've just gathered some data here. We've gathered the standard enthalpies of formation. Now, if you look closely, it's there, but it's a three-letter word here, but you don't want to miss it. We want to make sure that when we put these numbers into our calculators, we are accounting for all the standard enthalpies of formation for all the products minus the ones of all the reactants. So it is imperative that we account for the coefficients. Now, N2O4 is, you're thinking of this as 1 mole. So I'm even going to write the word 1 mole so you can see how moles cancel. Okay, so this ends up becoming 9.16 kilojoules. So that doesn't change at all. This, of course, is going to stay 0, as is the nitrogen. But here it's going to be important, very important, that you understand that there are 4 moles of H2O in this equation. So you're going to have to multiply that number by 4 moles. Notice moles will cancel. And so you're going to put 4 times negative 241.8 into your calculators. And you will get negative 967.2 kilojoules. All right, so now that we've accounted for the coefficients, we're ready to use the equation. The delta H, the enthalpy change for this reaction, is going to equal the sum of all the ones of the product. So we're going to add these two together. Negative 967.2 kilojoules. We're going to add those two together. Negative 967.2 kilojoules. And then notice here, this is a minus. And you know what? Frankly, every delta is always final minus initial. This is a delta just like anything else. So you should always remember products minus reactants, final minus initial. So minus, and then the sum of all the reactants, which in this case is just going to be 9.16 kilojoules. So minus 9.16 kilojoules. Be careful of your signs. Make sure you are accounting for all the signs correctly. So we're going to take negative 967.2. We're going to subtract 9.16. Everything is in kilojoules, and the answer will be negative 976.4 kilojoules. And that is going to be the enthalpy change associated with this reaction. And we can feel confident that it's correct. Now, we should be able to answer, is it exothermic or endothermic? How do we know? All you have to do is look at that sign. If you see a negative number right there, it's exothermic. It's going to release heat. How much heat? It's going to release 976.4 kilojoules for every 1 mole of N2O4 reacting with 4 moles of H2O. I'm sorry, H2. So that is how you would calculate delta H for any reaction using standard enthalpies of formation. Now, there are plenty of practice problems in the textbook. Let me give you some suggestions just to make sure that you can do these before you come to the exam. Question, I'm not sure if I've assigned it in the homework, but question number 87 would give you perfect practice to make sure that you can do these before the exam. This is on page 290, chapter 6, question number 87. Make sure you can do those before you come to the exam. All right, good luck with everything. See you later.